Let me remind you that we are thinking about Hamilton circuits. A Hamilton circuit in a graph is a circuit that visits each vertex just once. And we're looking at something called the traveling salesman problem, or simply TSP. That means, given a complete weighted graph, determine the Hamilton circuit of least total weight. In your recitation, you're going to solve the traveling salesman problem for the president of Ohio State, or the retired president, President Gee. And this problem is based on a graph of the Ohio State campuses, as I'm showing you on the right. It shows the 5 campuses and the distance between them. This is a complete weighted graph. You're going to use the following algorithm, 3-step algorithm. Step 1, list all possible Hamilton circuits. Step 2, well, let me just say, etc., because in this lecture I want to concentrate on thinking about that first step, step 1. The first step in the algorithm says you've got to list all the possible Hamilton circuits in your graph. So a natural question to ask is, well, how many are there? How many Hamilton circuits will we have to use if we follow this algorithm? Well, I happen to know that when you get to recitation and when you work on this problem there, you're going to have to find 12 Hamilton circuits. In fact, the handout that you will get for recitation will give you exactly 12 rows. So you know you need to fill that in with the 12 Hamilton circuits. But what if there were more vertices? How many more circuits would there be? For example, suppose we change the problem by saying that Gee also wants to visit the ATI campus in Worcester. Then we would now have a graph with 6 vertices. There would be more edges. Would there be more Hamilton circuits? You'd certainly think so, right? So to understand how this algorithm works, we want to ask what's going to happen in step 1. In other words, how many Hamilton circuits are there in a complete graph? Now, of course, the answer will depend on the number of vertices. So let's give that a name. The number of vertices in the graph will denote by the letter N. In the example for Ohio State, it's 5. In the example that you're looking at to the right, however, N is equal to 6. Now, before we decide how many Hamilton circuits there are in a graph, we need to agree about when 2 Hamilton circuits are considered to be the same. I've listed below in orange 3 different examples of Hamilton circuits. The first one is Columbus to Marion and so on, finishing at Columbus. The second one starts and finishes at Lima. The third one again begins and ends at Columbus. But I say that we're going to consider all 3 of those Hamilton circuits to be the same. Now, why is that? Well, first of all, let's compare number 1 and number 2. Okay, Hamilton circuit number 1 and Hamilton circuit number 2. So number 1 begins at Columbus and number 2 begins at Lima. They don't even start the same place. However, if you begin to compare them, notice that number 2 can be obtained from number 1 in the following way. Look at number 1, and rather than pointing to Columbus, point to Lima for your starting point. Okay? So from Lima, you would go to Newark. From Newark, you would go to Columbus. Now, since Columbus is also the first vertex, you can just say, oh, well, from Columbus, I want to go to Marion. From Marion to Mansfield. From Mansfield to Lima, and that's where I started. And notice that's exactly what you see in number 2. So it's really the same as number 1 with a different starting point. And we will therefore consider those to be the same Hamilton circuit, not as different Hamilton circuits. Likewise, let's compare number 1 and number 3. Well, if you start to compare those for a while, you realize, number 3 is number 1 read backwards, right? So number 1 goes Columbus, Marion, Mansfield, Lima, Newark, Columbus, but start at the right. Read it backwards. Columbus, Newark, Lima, Mansfield, Marion, Columbus, and that's exactly the same as number 3. So number 3 is number 1 done backwards or read backwards, but we'll also consider those two to be the same. So anytime we have two Hamilton circuits and they just differ by the choice of starting point, or they differ by the direction which we go around, forwards versus backwards, we'll consider them to be the same. Okay? So with that understood, we can now figure out how many Hamilton circuits there are in a complete graph. We'll do first of all the example of President Key visiting the Ohio State campuses. Well, of course, the president lives in Columbus. He has his office in Columbus, so he would always think of starting at Columbus. So let's do that. Now, if we want to specify a Hamilton circuit, we know we're going to start at Columbus, so we don't have to make any choices for that. The first thing we need to decide is, where do we go from Columbus? After leaving Columbus, where do we go? And you'll see that there are four possibilities, right? You can go to any one of the four regional campuses. So pick one. Let's say we go to Mansfield, beautiful Mansfield. And now you want to continue. Well, at this point, what are your options? You can't go back to Columbus. You can't remain in Mansfield. You've got to go to one of the other regional campuses, and now there are three possibilities. So now you have three options, and pick one. Let's say Newark. And now that you've visited Mansfield and Newark, what are your options? Well, you can visit either Marion or Lima. So this time there are only two options. Let's say we go to Lima. And now what are our options? Well, you might say you don't have any options at all, but let's instead say there's one. You've got to go to Marion. That's the one choice you have, and therefore you take it. And then finally, to finish up, you go back to Columbus. Now, as you do this, you're always free to make choices from among the options that are available to you. At first, there are four options. No matter what you choose, there will then be three options, and you're free to choose any one of those. And then, no matter what you've done, there will be two options. So you can freely choose these, and that means that there will be 4 times 3 times 2 times 1. That is to say, 24 possibilities. But we haven't yet taken into account the fact that we consider a Hamilton circuit done forwards to be the same as that same Hamilton circuit done backwards. Okay, there are two possible directions, and for that reason, we're going to say that there are not 24, but 24 divided by 2, in other words, 12 possible Hamilton circuits, just as I said earlier. The reasoning that we use to come up with this number is called the fundamental principle of counting. I'm going to have us take a look at a handout right now for a couple of other examples where we use that same principle. Well, what does the fundamental principle of counting say? It says if there are A ways of choosing a first thing, and then B ways of choosing a second thing, and then C ways of choosing a third thing, and so on, then the total number of outcomes is A times B times C times, and so on. So it involves multiplication, and for that reason, it's often called the multiplication rule. You can use this in any counting situation where you can structure the problem in the way that I've just said, making a first choice and a second choice and a third choice, where it's always true that the number of options you have is determined by where you are in the process. Well, that sounds awfully abstract. I think when you see it in action, you'll feel it's relatively simple. My first example is a method that used to be used for assigning license plates in the state of Ohio. Namely, in those days, an Ohio license plate consisted of 2 letters, followed by 2 numbers, followed again by 2 letters. Now, when I say number, I mean a single digit, and it can be anything from 0 through 9. It can be 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. Now, if you're going to have a system like that, of course, you want to know, do you have enough possibilities, right? If you have a license plate of this form, how many different license plates can there be? Well, it's actually rather simple to say, because if you were going to give somebody a license plate, if you're going to specify their plate, you could structure this as a series of choices. First of all, you would have to choose what to put down for the first letter. Well, there are 26 letters in the alphabet. You can use any letter at all, and therefore there are 26 possibilities. Following that, again, you need a letter. Again, there are 26 possibilities. When you come to the third position, however, you're supposed to use a number, and now there are 10 possibilities. Again, you need a number. There are 10 possibilities. Then you're back in the fifth position to using a letter. There are 26 possibilities. And finally, in the sixth and last position, there are 26 possibilities. Now, you can freely choose any letter, any number. There's no rule that says you can't repeat. You can just make these choices completely freely. So the number of possible license plates is this product, 26 times 26 times 10 times 10 times 26 times 26. Now, if you work that out, you'll discover it's somewhere between 45 and 46 million. That sounds pretty good. That's probably more than the number of vehicles in the state. All right, here's another example. There's a professor of theater named Professor Fahey, and he's gotten to a point in the rehearsal where he wants to tell 5 actors how to stand in a line across the front of the stage. Okay, he just wants them straight in a line, maybe pouring their hearts out individually to the audience. And how many different ways can he arrange them across the front of the stage? Well, let's think about the positions from left to right. He can put any one of the actors on the left, okay, in the leftmost position. So he points to the baritone and he says, okay, you stand there. Okay, now he comes to the next position. Well, now there aren't 5 possibilities because he's already used up one of the actors. Now he has 4. Okay, so he chooses one of the 4 actors and puts them in that position. He now comes to the center position. Having used 2 of the actors already, there are now 3 possibilities. For the next position, there are 2, and then finally there's a single actor to go in that last position. So the number of possible arrangements of his actors is 5 times 4 times 3 times 2 times 1, which is 120. Now I want to say a word about that number that we just saw, 5 times 4 times 3 times 2 times 1, in other words, 120. This kind of number comes up a lot in mathematics, this number that is simply the product of 5 and all the smaller integers. And mathematicians have a shorthand notation for it and a special name. The shorthand notation is what I'm showing you here. It's 5 followed by an exclamation point. And that doesn't mean, boy, I'm really excited by the number 5. What it means is this number here, 5 times 4 times 3 times 2 times 1. The name for it is 5 factorial. Now, returning to our problem of counting Hamilton circuits. In a complete graph with n vertices, how do we do that? Well, first note that just as President Gee has done, we can always start at a selected favorite vertex. That's not really a choice we have to make. We just say always we have a favorite vertex, and we're going to start there. So to specify a Hamilton circuit, you have to say what is the first vertex to visit after leaving your favorite vertex. And it can't be the favorite vertex itself. So the first number that you write down shouldn't be n, it should be n minus 1, right? You can visit anything except the favorite vertex. After that, having visited one vertex, now there are n minus 2 vertices left to visit, so now there are n minus 2 options. And then there are n minus 3 options, and then there are n minus 4 options, and so on. And you have to do that time after time after time, down to when you have only one option. So the number of Hamilton circuits is the product that I'm showing you here. it is n minus 1 times n minus 2 times n minus 3, and so on, all the way down to 3 times 2 times 1. But remember, this counts every Hamilton circuit twice because of the business about forwards and backwards. So in fact, we should divide by 2. So really, the number of Hamilton circuits in a complete graph with n vertices is n minus 1 times n minus 2 times n minus 3, and so on down to 3 times 2 times 1 divided by 2. As I've said, the number in the numerator is called n minus 1 factorial, which is written as I've shown below. And therefore, really, the correct formula is n minus 1 factorial divided by 2. Now, having developed that formula, we can now go back to what motivated us in the first place. Namely, if we were using this algorithm that asked us to list all the possible Hamilton circuits, how many would we have to list? Well, if there are 3 vertices and there's only one possible Hamilton circuit, what you should be thinking about there is you've simply got a triangle, and you've got to go around all the edges of the triangle. And because of our conventions, it doesn't matter where you start and which way you go. There's only one way to do it. If there are 4 vertices, if n is 4, then our formula gives us the number 3, right? That's 3 times 2 times 1 divided by 2, and that is 3. I want to actually show you those 3. Well, here you see the complete graph on 4 vertices, and I'm going to show you now those 4 possible Hamilton circuits. So one possibility is like this. As if you were going around a square. What else? Well, you could do this. And then the third possibility is like that. Okay. You notice I don't show you a starting vertex and an ending vertex, and I don't indicate a direction. That's because of our convention. So with our convention, taking one of these and starting at any vertex you like and going either direction, those are the only possibilities. There are 3 possible Hamilton circuits. All right, continuing to look at the values here, this table shows us again the number of vertices n and the number of possible Hamilton circuits in the complete graph. When we come to 5, well, we see the answer we already knew. If you have a complete graph with 5 vertices, then there are 12 possible Hamilton circuits. That's the number you will have to do in recitation. Suppose I included one more vertex. So suppose we included the Worcester campus, then there would be 6 vertices, and the number of Hamilton circuits would be 60. Oh boy, that would be a lot of work to list all 60 and then pick out the best one. For 7 vertices, there's 360. If you get to 10 vertices, there's over 181,000. And when you get to 15 vertices, there's more than 43.5 billion possible Hamilton circuits. Well, I hope you realize then that our algorithm is really quite silly. The idea of listing also all the possible Hamilton circuits is really quite hopeless unless the number of vertices is very small. In the recitation, I'm giving you the very biggest one that I possibly could in any reasonable way. I'm giving you n equals 5, and there's already 12 to be checked. Okay, so this really is a hopeless algorithm in practice. There are too many possibilities to check. We often call this sort of algorithm in which the first step is list all the possibilities. We call it a brute force algorithm.